Today I'm going to be talking to you about the gas kinematics in the circumgalactic medium traced by magnesium-2 and as a function of different galaxy types. So this work is in collaboration with my advisor, Chris Churchill, as well as Glenn Capsack, Michael Murphy, and Sebastian Trujillo-Gomez. So we've had a little bit of an introduction to the circumgalactic medium in a talk earlier today, but I figured I'd briefly explain it to you again. So we know the CGM is a large reservoir of multi-phase gas surrounding galaxies, and it contains the fuel for future star formation. We know it's pretty massive. It might contain the same amount of gas mass as that in the ISM of the galaxy itself. So to study the CGM, I actually used the quasar absorption line experiment, and I focused on the magnesium-2 absorption doublets. So there's been a lot of work done with magnesium-2 over the last several decades. We know that magnesium-2 is thought to be associated with accretion along dark matter filaments into the galaxy. It's also thought to be associated with outflowing material from the galaxy due to star formation or supernova feedback. And it's also possible that it's associated with satellite galaxies that are merging with the host halo. More recent work has been done to look at where magnesium-2 likes to stay around the galaxies, and it's been found that it's preferentially located along the major and minor axes of the galaxies, which is consistent with the idea of accretion and outflowing material. So for my talk today, I'm going to focus on what is the kinematic nature of gas in the CGM that's traced by magnesium-2, and how does it change as a function of galaxy type, because we know different types of galaxies have different processes occurring in them. So the main tool I'm going to use today is called the two-point velocity correlation function, which is the probability of finding any two clouds in the absorption. So here's an example profile, and you take the velocity separation of every pair of clouds. And so I should note that these are line of sight velocities, where 0 is the absorption redshift here. This also gives us a measure of the velocity dispersion of the absorbers that we're looking at. So previous works have used the TPCF to understand what's going on with the absorption in magnesium-2. Most recently, Jessica Evans, for her thesis, used 400 magnesium-2 absorbers and calculated this TPCF here, which is the gray shaded histogram. Previous works, including Jessica, fit several Gaussians to the TPCF to try and understand what's going on here. And I'd like to point out Churchill 2003 fit two Gaussians to their TPCF and attributed those to the vertical dispersion of gas in the galaxies themselves, and then the rotational motion around the galaxy. So one thing these previous works did not have was the actual galaxies associated with the absorption. They didn't know what galaxies were giving rise to the absorption. So I'm actually going to focus on whether these different Gaussians are due to the different galaxy types. Because I have a large sample called MgII, hence the cat. It's called the Magnesium-2 Absorber Galaxy Catalog. We have 182 isolated galaxies with detected or an upper limit of unabsorption. We have all kinds of different properties for them, including halo masses, colors, and redshifts. So I'm going to focus on a subsample of MgII, for which we have high-resolution, high-res or UV spectra, and there's 47 of these. And we have void profile fitted every one of these absorption profiles to get the velocity information. And we also use a Nikole sensitivity cut so that we can take into account the different quality of spectra among all of these pairs. So before I go into my results, I wanted to bring up some possible expectations we might see with these TPCFs for different galaxy types. So one of the cuts we did was in color. So for blue galaxies, we know that they have ongoing evolution where you have infalling material which causes star formation, which then triggers outflows. So maybe with the TPCFs, we'll see large internal absorber velocity dispersions due to these outflows. For red galaxies, they're commonly called red and dead because their star formation, the fuel for star formation has been shut off. So we don't expect to see infall and outgoing material. We also know that red galaxies tend to be located in more dense and more massive environments, so perhaps there's a lot of satellites surrounding these galaxies. So maybe we'll see smaller internal absorber velocity dispersions, but then when you're looking at the velocity dispersion of gas going around the galaxy, you'll see large dispersions due to these satellites. And then finally, we also split the sample by redshift to see if there's any redshift evolution, because we know star formation peaks at a redshift of 2 to 3, and I'm focusing at less than 1. And then the merging rates decrease with decreasing redshift. So perhaps we'll see smaller dispersions at lower redshift compared to higher redshift. So I mentioned a TBCF earlier. We use a slightly different version where we take, instead of the cloud velocities, we take all of the pixels in here and take pairs of pixels and do the velocity separations there. This gives us better sensitivity to the absorption, so if there are long wings in the absorption, we'll get those, and then we get more pairs for better statistics. So here are the TBCFs for the internal absorber velocity dispersion. And we have blue galaxies on the right, or left, and red galaxies on the right, split by redshift, and the cuts are here. And what you can see, in particular for the blue galaxies, there's no redshift evolution. All right, and then for red galaxies, we see the high redshift sample is similar to that for blue galaxies, but the velocity dispersion decreases at lower redshift. So this might be a little weird. I'll go into what this means in a little bit. So I just showed you the TBCF with respect to the absorption redshift. So here I showed you this. Then we can shift the velocities with respect to the galaxy. So 0 here is now the galaxy redshift, and the profile has shifted to the left a little bit. And then we can normalize the velocities by the circular velocity of the galaxy to try and take into account the mass of the galaxy. Since we're looking at all different kinds of galaxies, it's kind of important. So here is the TBCF with respect to the galaxy. So we're looking at the velocity dispersion of gas around the galaxy as opposed to within the absorber. So again, we have blue galaxies and red galaxies for different redshift cuts. And what you might notice is in both red and blue, the high redshift sample has a narrow velocity range, whereas the low redshift sample has these bumps out here with high velocities. So I should note that these bumps tend to include only 1 or 2 galaxies, so these bumps aren't very significant. Back to my expectations. I said that blue galaxies are expected to be evolving actively, whereas red galaxies are passively evolving, so maybe we should see the outflows and infall in blue rather than red. So the question then becomes, what is this stuff at low redshift? Well, possibly it's outflows in the blue galaxies. That might make sense. But then why do we have the high velocities in the red galaxies as well? This is kind of weird. Well, like I said before, we know that red galaxies tend to be in more overdense environments. So perhaps these bumps out here that we're seeing are due to satellites falling into the galaxy itself. And it's also possible that this bump out here is also due to satellite rather than outflowing material. All right, so if we focus just on the red galaxies, where we have the internal absorber dispersion here, and then down here on the bottom is the dispersion of absorption around the galaxies, we would expect that red galaxies will become more quiescent over time. They're dying, pretty much, rather than becoming more active. So then when you look at these plots, you might wonder, well, why do we see quiescence happening at lower redshift as opposed to higher redshift? Whereas down here, the lower redshift TBCF tends to have those more high velocity bumps. Well, perhaps what we're seeing down on the bottom plot is ancient outflows have stirred up the material with respect to the galaxy, and it hasn't settled yet. Whereas on the top plot, the actual absorbers themselves are actually settling down. So you have this material still going around the galaxy pretty fast, but the blobs themselves, the clouds, are pretty calm. And so to summarize, this one up here, for the internal dispersion of the absorbers, we see an evolution in the red galaxies where it's becoming more quiescent over time, while the blue galaxy absorber structures don't change over about a 2 gig-a-year time frame. So this may reflect ongoing evolution in the blue galaxies, whereas in the red, we might see passive evolution where it's just becoming more quiet. However, the dispersion of the absorbers around the galaxy at lower Z, perhaps we're seeing outflows or satellites. It's hard to say. One thing I should note for the TPCS, it's really hard to pick out what is actually going on because we're looking at line of sight velocities. And we're not even sure exactly where we're probing the galaxy because we only have an impact parameter, which is the minimum separation. So it could be any distance away. So it would be really helpful if some simulators could look into this and help untangle the processes giving rise to this velocity structure. So, thank you.
So you kind of introduced by talking about how the angle with respect to the minor major axis was an important part of how something might be out over. Is there any, were you able to probe with respect to axis ratio?
So,
with respect to positioning?
yeah, so we do have inclinations and position angles for most of these galaxies. I didn't show it here because that gets into a lot more stuff. But we do see differences with major and minor axes for blue galaxies. So the velocity dispersion tends to be greater along the minor axis, so where we expect outflows. But we don't see any difference with red galaxies. I haven't looked into the inclination yet.
Are there lines in your spectrum corresponding to the magnitude study things like the velocities and the ones that are further apart, just to get some sense whether you're a homogeneous one or a bimodal distribution?
Yeah, so the magnesium-2 absorbers are simultaneously fit with iron-2, manganese, and magnesium-1, but I haven't looked into any of those yet. That would actually be really interesting to figure out the metallicities and use that along with the position angles and dimensions. Yeah, future